The universe is home to planetary worlds that challenge our understanding of how planets form and evolve. The planets that shouldn't exist, but do, explores a fascinating range of exoplanets, from unusually puffy gas giants that might theoretically float on water to scorching super-Earths orbiting perilously close to their stars. These extraordinary worlds push the boundaries of planetary science, prompting us to rethink fundamental ideas about planetary formation and evolution. Their existence reveals that the cosmos is far more dynamic and complex than we once imagined. Tress 4b, the Puffy Giant. Tress 4b, often affectionately dubbed the Puffy Giant, defies conventional planetary formation models by presenting an enigma. A gas giant that is roughly 70% larger than Jupiter in radius, yet possesses less than a quarter of its mass. This enormous size, combined with its surprisingly low density, has led scientists to speculate that if it were placed in a giant bathtub, it would literally float on water. Such an extraordinary characteristic challenges our traditional understanding of how gas giants should form and evolve. The atmosphere of the Puffy Giant is very swollen, which is what makes it unique. Standard models of planets say that a planet with its mass should be much more compact, with the gaseous shell being squished together into a tighter shape by gravity. However, studies show that the Puffy Giant's outer layers are much longer than thought. This swelling is probably caused by the strong stellar light from its mother star, which is close by. The planet is very close to its star, so it is constantly hit by high-energy photons that heat its atmosphere and make it grow. Because of this, heat inflation happens, which makes a huge puffy package and lowers the total density. Because of this, the planet's air pressure gradient is extremely low, which lets heat spread over a large area. The unique atmospheric properties of the Puffy Giant have significant implications for its internal structure and evolution. Researchers suggest that the planet's low density could be indicative of a modest core surrounded by a thick, extended envelope of hydrogen and helium. In contrast to denser gas giants, where a large core helps bind the overlying gases, the Puffy Giant appears to have a comparatively minimal core. This scenario raises intriguing questions about the planet's formation history. Did it form in an environment with less available solid material, or did processes such as core erosion or inefficient accretion lead to its current state? Spectroscopic studies have helped us learn more about the atmosphere of the Puffy Giant. By looking at its spectral lines, we can get a sense of chemical species that are common in hot, radioactive places. For instance, signs of water vapor, carbon monoxide, and even strange substances can be found. These give us hints about the chemical processes that are going on in harsh conditions. Because these molecules interact with the planet's expanding atmosphere, there is a complex balance between radiation heating and cooling that makes the planet even more swollen. Dynamics of the Puffy Giant offer a fascinating case study in atmospheric circulation under intense irradiation. Models suggest that strong day-to-night temperature contrasts drive powerful winds, redistributing heat across the planet's surface. These winds are capable of transporting material from the scorching day side, where temperatures can soar dramatically, to the cooler night side, thereby affecting the overall energy balance and even influencing the chemical composition in different regions of the atmosphere. Cororo 7b, the Scorched Rock. Cororo 7b, also known as the Scorched Rock, is a very fast-period rocky planet that tests how long life can last on a world. This world is in a very close orbit around its mother star, so it is constantly bombarded by stellar light, which not only heats its surface to very high temperatures, but may even turn some of its crust into gas. Because it is so close to its star, its circular period is only hours. The planet is in an environment that is nothing short of catastrophic by Earth standards. The intense heat that the scorched rock gets is what makes it so interesting. Models show that on the side that gets the most sun, temperatures could rise so high that they melt rock, leaving behind a burning, molten landscape that is always changing shape because of the extreme heat. When the radiation is this strong, volatile materials on the surface can be turned into vapor and then blown away by strong star winds. This creates an atmosphere that is mostly made up of rock vapor as it changes over time. Our knowledge of the stability and makeup of hard planets is being tested by this process, which makes us wonder how such a body can keep its surface stable over astronomical timescales. There are also big effects on the scorched rock's geology and atmosphere because of its harsh conditions. Because the planet's spin is probably locked to the tides, it always faces the same way toward its star. This means that one side is always daytime, and the other is always nighttime. Because of this contrast, there is a huge difference in warmth between the day and night parts. On the day side, it's a scorching fire where silicate materials may melt or even evaporate. At night, it might be cold enough for any rock that has been evaporated to return to its solid form. These big differences cause strong winds as the planet tries to move heat around, which could lead to a dynamic, if thin, atmospheric circulation system that doesn't make sense for a rocky body. The detection of specific absorption features indicates the presence of metal vapors and other refractory elements in its atmosphere, substances that would not normally be seen on a cooler, more temperate, rocky planet. These spectral signatures provide critical clues to the composition of the planet's surface and the processes that dominate in such an extreme environment. The fact that rock itself might exist in both liquid and gaseous forms on the scorched rock not only complicates the traditional classification of rocky planets, but also hints at the potential for transient exotic phenomena that challenge our models of planetary evolution. The discovery of the scorched rock brings up important questions about how rocky planets so close to their stars grow and how they stay alive over time. According to the usual ideas about how planets form, protoplanetary spheres would either not have enough matter or be too rough for a stable planet to form in the middle of them. Just the fact that the scorched rock exists suggests that either our models need to be improved or that there are new, possibly violent ways that planets form, like moving inward after forming farther out in the disk or the shell of a planet that used to be bigger being torn off. Wasp 76b, the Iron Rain planet. We called Wasp 76b the Iron Rain planet, and it has some of the strangest weather we've seen on other planets. This hot Jupiter moves very close to its star home, which makes it over 2,400 Kelvin during the day. When it gets this hot, the Earth's atmosphere can get so thin that heavy things like iron can be turned into air, while the night side of Wasp 76b is much cooler because it is shielded from direct star radiation by the tides. This lets drops of iron gas form that can fall as rain. We thought this strange process wouldn't happen, but it does. It makes us question what we think we know about the chemicals that are in the atmospheres of gas giants and how they work. The huge difference in temperature between the side that is hot during the day and the side that is cooler at night is caused by Wasp 76b's close rotation and tidal locking. In other words, one half of the world is always facing its star, while the other half is always dark. On the day side, the constant radiation from stars heats the atmosphere so much that even hard materials that are usually solid are turned into gas. In Earth's atmosphere, iron is a solid at room temperature, but in Wasp 76b's high atmosphere, it is a gas. But as winds carry this iron-rich gas toward the night side, the temperature drops sharply, making the mist solidify. This creates an atmosphere cycle that is unlike any other in our solar system. During the day, water evaporates, and at night, water condenses, creating a phenomenon that is well known as iron rain. Astronomers have found specific absorption lines that show charged iron by looking at the light that goes through and comes out of Wasp 76b's atmosphere. These results show that the very high temperatures on the day side are enough to turn metals into air. As the air moves across the terminator, which is the line between day and night, it quickly cools down, which makes iron droplets form. Then, these drops are seen indirectly by looking at how they change the opacity and emission patterns of the atmosphere. The discovery not only shows how strange the atmospheres of other planets can be chemically, but it also tests models of how heat is distributed and chemical balance in very hot gas giants. The strong winds that move heat around Wasp 76b's surface make the physics of the atmosphere even more difficult. This side of the planet stays very hot during the day, but how quickly heat moves to the cooler night side depends on how well the air moves. Based on the most recent data, current models show that some redistribution of heat does happen, but it is not enough to make the temperature uniform everywhere. The cycle of ion vaporization and condensation is kept going by this constant imbalance. This makes Wasp 76b a great place to study the physics of extreme atmospheres. GJ 1214b, the Misty mini Neptune. At first view, GJ 1214b looks like an exoplanet in the middle of the range. Based on its size, this type of world probably has a mostly rocky makeup. However, studies have shown that its atmosphere is not only very thick, but also mostly made up of layers of hydrogen, helium, and maybe even water vapor. The low general mass of the planet is due to this envelope. This makes the planet look much more puffy than its core would suggest. Because of this, the traits show that GJ 1214b is in a transitional category, which makes it hard for us to neatly put exoplanets into established groups. The thick atmosphere of GJ 1214b has significant implications for its thermal properties and weather dynamics. Given its close orbit around its host star, the planet is subjected to intense stellar irradiation. This energy input heats the upper layers of its atmosphere to temperatures that could drive vigorous circulation patterns. Such dynamics might lead to a complex system of winds and temperature gradients, which in turn affect the chemical equilibrium of the atmosphere. Spectroscopic studies have provided evidence of water vapor and other molecular species, hinting at a possible water world scenario beneath the hazy layers. The presence of water vapor in particular has spurred debates about the potential habitability of similar exoplanets, though GJ 1214b itself remains far too extreme for life as we know it. The past of how GJ 1214b came to be is currently being studied. Its presence suggests that it may have formed in a place where conditions were right for a large gaseous envelope to form, even though the core did not hit the critical mass that is usually needed for gas to start accreting out of control. It's possible that GJ 1214b is a failed gas giant. A planet that started to gather gas but couldn't grow any bigger because the protoplanetary disk broke apart, or other dynamic processes took over. Instead, it could have started out farther away from its mother star and moved closer, keeping its thick atmosphere even as the star's radiation got stronger. Transmission spectroscopy of GJ 1214b's atmosphere has been made possible by observations made with the James Webb Space Telescope and other new tools. Astronomers have found the absorption traits of different molecules by looking at the sunlight that passes through its atmosphere during transits. These results help define the makeup of the atmosphere, its size, and the area that clouds might cover. They also give us clues about the physical processes that control its wider range. In this way, GJ 1214b is a very important standard for checking how well models of how atmospheres change on low-mass, highly radioactive worlds work. Kepler 78b, the Forbidden Earth. A planet with Earth-like mass, but unlike anything Earth-like in temperament. Kepler 78b is almost a cosmic joke, an object that has no right to be where it is, yet somehow, impossibly, it's there. Most exoplanets follow a script. This one rips it up and sets it on fire. It orbits its star in just 8.5 hours. Not days, hours. You could eat dinner, sleep, and wake up on Kepler 78b, and an entire year would have passed. If you brought a calendar, it would be obsolete before breakfast. This orbit is so tight, so irrational, that Kepler 78b isn't really orbiting in the traditional sense. It's free-falling in a circle, trapped in a constant near-death experience just shy of the Roche limit, the invisible line where gravity pulls celestial bodies apart. Things are getting worse. The day side of the world gets as hot as 3,000 degrees Celsius, which is unthinkable. It's warmer there than on the surface of some stars. Hot enough to turn rock into steam. Models that are based on ideas say that the surface is made up of magma seas and very hot metal clouds. But the side at night? It might be cold enough for metal rain to form from rock gas. It's possible that melted iron could fall from the sky in storms. Still, it's about the size of Earth. Same amount of mass and density. That's the catch. It feels safe in the wrong ways. It looks like Earth, but it's burning with the anger of a system that didn't work right. The real puzzle in space is that Kepler 78b shouldn't exist. Planets don't form this close to their stars. Too many fights, too hot, and too much chaos in the area. At this temperature range, solid matter can't form in protoplanetary spheres, which are where planets are born. What's going on? Either Kepler 78b formed far away and moved toward us, surviving a series of gravity dangers, or we don't understand how planets really form. Planetary migration isn't rare, but for a rocky world this small to migrate this close without being torn apart, that's rare. So rare, in fact, that simulations trying to model this scenario often just fail. Flatline. Dead ends. Kepler 78b doesn't just bend rules. It breaks the engines that write them. What if it didn't move, though? One other idea is a lot scarier. We may be seeing the heart of a planet that used to be like Neptune that has been stripped away. A world that used to be big and full of gas, but radiation tore away its top layers until only its IMTAL skeleton was left. It really is a ghost planet, the remains of something huge that is now just a burning cinder. The feeling of isolation is far more terrifying. At least, we haven't found any planets in its system that are twins. Some models say it may have had neighbors in the past, maybe even a system of planets that were very close together. But planets fight when they move inward this quickly. They eat each other. They throw each other into space or toward the star. Kepler 78b could be the only being left alive in a planetary cage match. And then there's the force of magnetism. Scientists are trying to figure out if the closeness of Kepler 78b to its star causes electromagnetic interactions that are strong enough to make the star spin. Think about a world that is so close to its sun that it moves the surface of it. That's not just artistic hyperbole, that could be science. There's also a niche curiosity in its light curve, the dip in brightness we observe when it passes in front of its star. These measurements are used to study composition and atmosphere, but Kepler 78b's light curve is unusually sharp. It hints at a lack of atmosphere, yes, but possibly more. There's speculation about reflective mineral clouds or metallic gas halos forming and dissipating in real time. It's not just passing in front of the star, it might be shedding parts of itself as it goes. Let's look at the night side once more. Normal heat exchange doesn't work right at these temperatures. If there is an atmosphere, it might be too thin or too disorganized to move heat around well. That means a permanent split between day and night. On one side, there is a rolling fire. The other could be a dark, cracked surface that gets better after short periods of cool weather. They call it a tidally locked inferno, but it looks more like two different hells. It's simple to get lost in the crazy world we live in. The most scary thing about it, though, is that it is dying. Slowly, Kepler 78b is moving toward its star. The number of years it has left may be very low. In the grand scheme of things, that's just a blink. We are seeing the last part of a planet's life. It didn't have a beginning or an ending. It had a long, dramatic finish. That doesn't happen often. Planets are often found a long time before or after this stage. Kelt 9b, the ion wraith. It's not going around a star. It goes around a stove. But Kelt 9b isn't just hot. It's also against matter as we know it. Kelt 9b has ripped those rules out, burned them, and thrown the ashes into space. Most planets follow the rules of chemistry and gravity. Things get stranger as you zoom in. In the high atmosphere, there is a certain layer where science doesn't make sense. It's too cool for full activation and too hot for molecules to stay alive. This area in between is a whirling hell of half-formed atoms, and nothing stable wants to stay there, like the edge of a storm where there are no rules. Scientists have confirmed the presence of atomic iron and magnesium gas freely floating through the atmosphere, not as part of a mineral or cloud as individual atoms. Imagine walking outside and inhaling a breeze made of vaporized cutlery. That's the vibe. Let's talk about getting away. Kelt 9b is not only hot, it's also boiling. Its gas is leaking out into space, leaving a comet-like trail. Helium, hydrogen, and metal fumes are all going. Every second, millions of tons of mass are lost. It has a tail, but not because it's moving quickly. It has a tail because it's being taken apart. You'd think all that heat would at least distribute evenly. But no. Kelt 9b is tidally locked, with one side permanently facing its star and the other forever in darkness. Normally, planets like this develop supersonic winds that move heat around, but Kelt 9b is so extreme the winds can't keep up. The day side remains brutally scorched. The night side is slightly less scorched. The heat is stuck. A sliver of electromagnetic brilliance might exist. The high atmosphere is full of ions, so it acts like plasma. Magnetic fields and plasma can change each other. Some scientists think that Kelt 9b might be making a plasma-driven magnetic shield, which is a brief force field that keeps the atmosphere from escaping. It's like duct taping your skin during landing, but for planets. This isn't just a gas giant, it's a balloon on the brink. With nearly twice the radius of Jupiter and just slightly more mass, its density is so low, it's like fluff. The heat is inflating it, stretching it out to absurd dimensions. If it gets any hotter, it might simply lose cohesion. Think. Gravitationally embarrassed. And if you think it orbits a friendly sun, think again. Kelt 9b circles an A-type blue-white star, massive, young, and deadly. These stars are short-lived and aggressive, spitting out ultraviolet radiation like cosmic napalm. A-type stars are so hostile, we don't even expect planets to survive this close. Yet there it is, Kelt 9b, clinging to life while its host star actively erases it. Its path? Totally too tight. Only 1.5 days for each turn of the Earth. You could have a coffee and enjoy the start of a new year. Since it's so close, it gives off light instead of reflecting it. Invisible light. Kelt 9b shines. Most worlds get their light from the stars. We can directly see Kelt 9b's spectrum because it shines like a dead star. This glow tells us a lot. It's one of the only exoplanets with a visible light emission spectrum, revealing not just its heat, but its ingredients. Not clouds, not storms, but elements. Bare, exposed, and naked in the light. Before its discovery, scientists didn't even believe gas giants could exist in such extreme conditions. Kelt 9b shattered that assumption. It was so out of line that we had to create a whole new category, ultra-hot Jupiters. Planets that blur the line between planet and star. Objects that shouldn't exist, but somehow burn their names into the observational record. The light curve data, the way its brightness dips when it crosses in front of its star, also shows strange sharpness. That might be because its atmosphere is being stripped so fast that it forms a tight, sharp-edged silhouette like a knife's shadow. It could even be shedding a thin metallic cloud as it moves, whispering its own slow demise into the cosmos. It's not our business how it got there. It might have begun farther away and wound its way inward. It could have been thrown in by a planet sister that is no longer there. It could have formed right there, in the pot of fire. It would have been a mathematical wonder. These ideas don't work well together. None of them fully explain it. I think that's what makes it so amazing. Some think it's spiraling inward. Tidal interactions with the star could eventually pull it into a final fatal embrace. It's possible we're watching Kelt 9b in its last million years of existence. A slow-motion planetary execution, and through it all, it shines. Not just in a figurative way, it has a clear glow. It tells its story right into the light we catch in a way. There is a planet that shouldn't be there, but sends a signal that can be seen hundreds of light years away. Wasp 107b, Hollow Titan. Rather than going around, it floats. Wasp 107b is almost as big as Jupiter, but it only has a tenth as much mass. If you dropped it into a pool big enough, it might float because the planet is so puffy, light, and unlikely. This isn't just a trick for parties, though. It's an identity problem on a global scale. Its average density, about 0.13 grams per cubic centimeter. For context, that's lighter than cotton candy, less than Saturn, and only marginally more dense than air on Earth at high altitude. Wasp 107b is, for all practical purposes, a gravity-defying gas balloon. The more you dig, the weirder things get. According to the standard explanation of how planets form, a gas giant needs a core that is at least 10 times the mass of Earth in order to attract a huge sphere of gas. But Wasp 107b might have a core that is only 2 Earth masses thick. That shouldn't be enough to turn into this planet. Still, there it is. It doesn't follow the core mass threshold, which changes the rules for how gas giants grow. A secret force could be making it bigger. Astronomers think that tidal heating, internal friction caused by the star's gravity pulling on it, is what's happening. But ohmic warmth is an idea that goes into the strange. That's when charged particles in the atmosphere interact with magnetic fields. This makes the planet warmer from the inside by causing electrical resistance. Wasp 107b might be a gas bubble with an electric heart. And the atmosphere? It's a lab of extremes. Observations from Hubble and JWST have detected helium, water vapor, and even hints of metal hydrides. Exotic molecules like titanium hydride, TiH, and chromium hydride, CrH, which are usually seen in brown dwarfs, not planets. In other words, Wasp 107b's atmosphere is acting more like a failed star than a traditional gas giant. Things get even more complicated by photochemical hazes. These very small particles take in ultraviolet light, which could change the color of the planet's upper atmosphere. They change not only how the planet reflects light from stars, but they may also mess up spectral readings, making it hard to say for sure what the planet is made of. Wasp 107b might not just be hiding behind clouds, it might be trying to trick our detectors. Our only certainty is that it's leaking. Helium has been seen fleeing at speeds faster than sound. This means that Wasp 107b is the first world whose helium output has been directly found. Helium builds up into a big, long cloud that floats around the Earth like a sparkling aura of loss. Still, this isn't a disaster. The sound is eerie and soft, like a scent mist floating off into space. Its tight orbit, just 5.7 Earth days, should in theory mean it gets roasted by its star, especially with such low density. Gas should be blown off in waves. But the planet is still there. It may be distorted, stretched, perhaps even ablate. Some models suggest it has a teardrop shape caused by tidal forces, which would make it one of the few non-spherical planets ever observed. We also don't know for sure if its structure is stacked yet. A thick core that is surrounded by layers of hydrogen, helium, and clouds. The core could be small or bigger than we think. The atmosphere isn't a flat sheet. It could be a bunch of swollen shells that look like hot, clear onions. The fact that Wasp 107b is on the planetary spectrum makes it even more interesting. It's kind of in the middle of being a sub-Neptune planet and a gas giant planet. It could be the missing link or even the natural middle ground between small worlds with lots of ice and Jupiters. It's not just a strange case, it's a model for how planets might become giants or not. New studies also show that its light might change, but not because of its star. It might change because of itself. Moving cloud bands, changing hazes, or short-lived weather events in its extended atmosphere could cause changes in albedo, reflectivity. If this is true, it would be one of the first exoplanets with a face that flickers and changes how it reflects light as it goes around the sun. 55 Canri E, the diamond planet. 55. Canri E, also known as the diamond planet, is one of the strangest and most interesting super-Earths in our galaxy. As this ultra-short period planet orbits dangerously close to its mother star, conditions are so harsh that tidal locking is almost certain to happen. One hemisphere is always in sunshine, while the other is always in darkness. This creates a huge difference in temperature and chemistry that questions common ideas about how planets evolve. It is thought that temperatures will soar during the day to levels that can melt rock, possibly hitting 2,700 Kelvin or higher. This much heat is enough to turn silicates and metals into gas, which changes the surface conditions drastically and causes strange natural processes to happen. The strong radiation from stars not only wipes out any possible atmosphere, but it also creates a changing climate where the surface could constantly go from being liquid to gas. The night side, on the other hand, might have a huge drop in temperature because it is not directly hit by star radiation. This might allow some of the melted materials to solidify again. This constant contrast not only describes the planet's physical state, but it also sets the stage for interesting processes in which the atmosphere moves and heat is distributed that are still being studied. Based on its mass, radius, and density, some studies propose that the planet may be carbon-rich, a characteristic that has sparked speculation about the presence of diamond or graphite in its interior. In such a scenario, the extreme pressures within the planet's core could potentially crystallize carbon into diamond, giving rise to the evocative nickname, the Diamond Planet. While the exact nature of its internal structure remains a topic of debate. The possibility of such an exotic composition challenges our understanding of planetary chemistry and raises profound questions about the diversity of material compositions in rocky exoplanets. Spectroscopic readings and measurements of the thermal phase curve have been very important in figuring out what's going on at 55 Canri E. Astronomers have learned about the chemicals that are on the planet by looking at how light passes through any clouds that are still there or bounces off the surface. The planet is very close to its star, which means it gets a lot of radiation. This makes it hard to get accurate data, but what we do know points to a volatile and biologically complex environment. When very hot gases interact with each other and may be escaping from the planet's core, they may create short-lived changes in the atmosphere that reveal important details about its evolutionary past. The very existence of 55 Canri E poses significant challenges to traditional theories of planetary formation and survival. Models of planet formation typically predict that rocky planets orbiting so close to their stars should lose much of their mass or even disintegrate under the extreme tidal forces and radiation. Yet, 55 Canri E not only endures, but also appears to be in a stable, albeit harsh, configuration. This suggests that alternative formation scenarios, such as inward migration from a cooler, more distant orbit, or the survival of a remnant core after significant atmospheric stripping, may be at work, thereby enriching our understanding of planetary system evolution. GJ 436b, the evaporating hot Neptune. GJ 436b, which is sometimes called the evaporating hot Neptune, is an interesting planet that goes against what we think we know about how stable and long-lasting atmospheres are. This planet is very close to a red dwarf star and is being irradiated by the star very strongly. This is slowly removing its hydrogen shell. Observations show that GJ 436b is losing mass at a rate that makes it leave behind a long, comet-like tail of gas. This is not what you would expect from a world the size of Neptune. GJ 436b is interesting because it has a tricky mix between being held together by gravity and being dominated by star radiation. The planet gets a lot of energy from its mother star because its path is so close to it. This energy raises the temperature of the higher atmosphere to very high levels, which makes the hydrogen atoms move faster than the planet's escape velocity. Because of this, GJ 436b's top layers are constantly being pulled off and sent into space. Not only does this mass loss change the planet's atmosphere over time, but it also makes us wonder how hot Neptunes in similar settings will change over time. By carefully analyzing the light that filters through the planet's extended atmosphere, astronomers have detected clear signatures of hydrogen and other lighter elements escaping into space. These observations confirm that the planet is experiencing significant atmospheric erosion, forming a giant diffuse tail that extends far behind it as it orbits its star. The detection of this tail is particularly compelling because it provides direct evidence of a dynamic process that was once only theorized. The presence of ionized hydrogen in the tail also suggests that stellar winds are playing a significant role in accelerating the mass loss, further complicating the balance between the planet's gravity and the external forces acting upon it. There are also important clues about how GJ 436b formed and how it evolved in its physical features. The planet may have been bigger or had a thicker atmosphere in the past, based on its relatively low density and signs of ongoing atmospheric escape. Over time, the constant barrage of star energy has worn away at its envelope, leaving behind a structure that shows signs of its exciting past. Models that say worlds the size of Neptune should be better able to handle such harsh conditions are called into question by this evolutionary situation. Instead, GJ 436b makes us think about how the atmosphere stays in place, moves, and how star activity affects the surroundings of planets. Studying GJ 436b gives us a better idea of how the atmospheres of other worlds change over time. By comparing what scientists have seen of this hot Neptune to what they have seen of other planets like it, they can learn more about how star irradiation changes the makeup and stability of the atmosphere. The case of GJ 436b shows how important it is to think about things like the spectral type of the host star, the planet's magnetic field, and the chance that stellar wind will interact with the atmosphere when making models of planets. Kepler 10c, the mega-Earth. Kepler 10c, which is often called the mega-Earth, questions the way we think about earthly worlds in general. This object is much bigger and heavier than most super-Earths, which goes against what people think they would expect. It blurs the lines between hard planets and gas-filled mini-Neptunes. Because it exists, we have to go back and improve our models of how planets grow and what they are made of inside. It looks like this mega-Earth is a rocky body that should have gathered a lot of gas when it formed, based on its mass and size. It is mostly rocks, though, and the density is surprisingly high, according to what has been seen. This means that either it took in a huge amount of heavy elements during its early years, or lost a lot of its lighter, more volatile material over time. Most scientists think that strong radiation from stars and strong tides may have eaten away a once stronger atmosphere, leaving behind a thick, solid core. To this end, Kepler 10c is a truly amazing natural experiment that shows that planets that start out with a lot of gas can change over time into things that are mostly made of rocks. If something has a high density, it means that it is full of heavy elements like iron and silicates. This suggests that it has a layered structure with a large metallic core surrounded by a silicate shell. The mass and radius of this object lead to detailed modeling that shows its core-to-mantle ratio may be very different from that of Earth and other smaller rocky planets. This difference makes us think about how differentiation works when planets are being formed. Also, the planet doesn't have a thick atmosphere like planets of the same mass should have in normal models. This brings up important questions about how volatiles can be removed or kept from building up in high radiation settings. The detection of specific absorption features in the reflected light spectrum provides clues that the surface is primarily composed of refractory materials, with little to no volatile components. These findings support the notion that Kepler 10c has undergone significant atmospheric loss, a process that might be common for planets in close proximity to their stars. The implications of this process extend beyond this individual world, as it forces theorists to re-examine the evolutionary pathways that lead to such dramatic outcomes. Kepler 10c's orbital mechanics are just as interesting as what it is made of on the inside. Because it orbits its star so close, it is exposed to strong tidal forces. These forces can cause tidal locking, a condition in which one side always faces the star. This makes huge differences in temperature between the day and night sides, which affects how the rocks and air have changed over time. Since there isn't much of an atmosphere, it's likely that these extremes are felt directly on the surface. This also means that tidal heating could be causing ongoing geological activity. In theory, these kinds of processes could cause small areas of partial melting or even slow, plate-like shifts over geological timescales. Towi 849b, the naked core. Towi 849b, also called the naked core, shows an amazing picture of what's left of a once powerful gas giant after its atmosphere is stripped away. This extrasolar planet has a core that is thick, rocky, or metallic, and it shows us a stripped-down residue that makes us question how planets form and evolve. Since this world orbits its star very close, it doesn't seem to have the thick, volatile layers that usually make up gas giants. This gives us a rare look into the workings of a planet that should have, by all accounts, kept its huge atmosphere. The amazing process of air erosion is at the heart of this event. Standard models of how planets form say that gas giants form with thick shells that take in hydrogen and helium from the protoplanetary disk around them. But in the case of Towi 849b, these upper layers have probably been worn away by strong star radiation and tides. The result is a core that is empty and thick, very different from what it used to be. This huge change makes us think again about the delicate balance between keeping and losing atmosphere, especially for planets in very far-away orbits. The fact that Towi 849b doesn't have a thick layer of gas shows what it's really made of. A body full of heavy elements like iron and silicates that would usually be hidden by hundreds or even thousands of kilometers of gas. Because the planet is so close to its star and there is a lot of glare, it is hard to make direct readings. However, small absorption features in the planet's spectrum suggest that its surface is mostly made up of refractory materials. The fact that there are no spectral marks for volatile molecules supports the idea that Towi 849b has lost a lot of energy in the atmosphere. The light we see doesn't show a scattered envelope. Instead, it shows a dense, compact world that looks more like the core of a planet than a normal gas giant. Its close orbit subjects the planet to relentless tidal forces, which not only contribute to the stripping away of its atmosphere, but may also induce internal heating. This tidal heating could drive geological activity within the core, leading to localized areas of partial melting, or even tectonic shifts over geological timescales. Such processes are significant because they offer clues about the internal structure and long-term evolution of planets that have been exposed to extreme stellar environments. The survival of Towi 849b in such a harsh setting suggests that the mechanisms governing atmospheric loss and core retention are more complex than previously thought. It raises the possibility that many more planets might exist in a similar naked state, their true natures hidden beneath layers that were once much thicker. LTT 9779b, the Desert Survivor. The planet LTT 9779b, also called the Desert Survivor, is an amazing example of an extremely hot Neptune going against the odds by living in a place where strong stellar irradiation would usually wipe out a planet's atmosphere. This extrasolar planet orbits in the Neptunian desert, which makes it hard for us to figure out how atmospheres stay in place and how planets change over time. Even though its host star sends out a lot of radiation, LTT 9779b is able to keep its thick, warm shell. This makes it stand out from its peers. Located so close that the intense stellar flux should, in theory, erode its atmosphere over time, LTT 9779b instead exhibits a robust, if counterintuitive, resilience. The high levels of irradiation heat its atmosphere to searing temperatures that would typically drive rapid atmospheric escape in Neptune-sized planets. Yet, observations suggest that the planet maintains a significant gaseous envelope, defying conventional models which predict that such a planet should be stripped bare and left as a rocky core. This resilience raises compelling questions about the mechanisms that allow LTT 9779b to endure in such a hostile environment. One possibility is that the planet's gravity, though relatively weak compared to larger gas giants, is just sufficient to retain its volatile constituents against the intense stellar winds and radiation pressure. Alternatively, LTT 9779b might possess an internal energy source, perhaps residual heat from its formation or ongoing tidal interactions with its star, that helps counteract the loss of atmospheric mass. The balance between these forces is delicate, and understanding it is crucial for refining our models of atmospheric escape and retention in extreme exoplanets. The atmosphere of LTT 9779b has been largely figured out with the help of spectroscopic data. Astronomers have found signs of water vapor, carbon monoxide, and other molecular species that describe its chemical makeup by looking at the absorption lines in its transmission spectrum. The results of these tests show that the planet's atmosphere is chemically rich and actively active, even though it may be because of how hard the conditions are. The chemical abundances found give us important information about how the planet formed. They show that it may have started out further out in its star's system and then moved closer to where it is now, which is a dangerous orbit. Infrared studies that were very thorough show that LTT 9779b's atmosphere has a shape that suggests complicated wind patterns and temperature differences. The interaction between the very hot areas during the day and the cooler areas at night seems to drive strong air circulation, with fast winds moving energy around the world. Wasp 12b, the inescapable Inferno. Many people call Wasp 12b the inescapable Inferno because it is one of the hottest Jupiters. This gas giant will orbit its star in less than 1.1 days and is quickly spiraling in towards its parent star, where it will be absorbed. The constant pull of gravity and intense radiation from stars that make up its path make us question the way we usually think about how planets survive and change. The dramatic ending of this world makes us think again about how tides and air erosion work in very close orbits. In the harsh environment of Wasp 12b, the day side is bombarded with an almost overwhelming intensity of stellar energy. Temperatures soar to levels that can exceed 2,500 Kelvin, a searing heat that not only inflates the planet's atmosphere, but also creates an environment in which its very structure is under constant strain. Under such intense conditions, the gas envelope expands dramatically, leading to a bloated appearance that has earned the planet its nickname. Its extremely low density is a paradox. Despite its massive size, the extended atmosphere contributes little to its overall mass, making it a puff in an otherwise dense planetary family. The high heat that Wasp 12b goes through is a big reason for its bloated state. Its upper layers of atmosphere are getting bigger because it keeps taking in high-energy photons from its star. As these layers get thicker, gravity starts to lose its grip on them, and they start to fall into space. This could finally cause the atmosphere to be completely stripped away. Tidal forces make this rapid inflation even worse. Because the planet is so close to its star, it is subject to very strong gravity stresses that change its shape even more and speed up its orbital decay. So, Wasp 12b is not only physically swollen, but it is also dynamically unstable. As it moves closer and closer to the star's surface, it will slowly fall apart. Observational data obtained through transit spectroscopy have revealed key insights into the atmospheric composition of Wasp 12b. Analysis of its transmission spectrum has uncovered the presence of water vapor, carbon monoxide, and other trace elements, painting a picture of a chemically complex and highly irradiated atmosphere. The spectral features suggest that the extreme temperatures facilitate the ionization and dissociation of molecular bonds, leading to a mix of neutral and ionized species. These findings challenge our understanding of chemical equilibrium under such intense conditions, as the interplay between radiation, temperature, and pressure creates a unique atmospheric chemistry not seen in cooler gas giants. The way Wasp-12b's path has changed over time is a good example of how life ends on planets with harsh conditions. Its orbit is getting smaller, which means that the planet is slowly being eaten by its star. This could be seen directly by scientists as real-time proof of tidal disruption and mass transfer. Scientists can improve their predictions about what will happen to other nearby exoplanets in the long run by using this situation to put limits on their theoretical models. HD 106906b, the Distant Wanderer. HD 106906b, also known as the Distant Wanderer, is an exoplanet that lives over 700 astronomical units away from its home star, which goes against most ideas about how planets form. These huge differences challenge the usual ideas about how protoplanetary disks form and how planets move around, which is making scientists rethink where and how big planets can form. At such an extreme distance, this object exists in a realm where the gravitational influence of its star is exceptionally weak. Traditional theories predict that planets form within the dense regions of a protoplanetary disk, where material is abundant enough to build up significant mass. However, the location of the Distant Wanderer lies far beyond the expected edge of these disks, suggesting an alternative formation scenario may be at work. One possibility is that it formed closer to its star and was later flung outwards through dynamic interactions, perhaps via gravitational encounters with other massive bodies in the system. Another theory proposes that it may have formed in situ through the rapid collapse of a fragment in the outer disk, although such a mechanism remains less understood. Its large separation from the host star means that its emitted and reflected light can be observed without the overwhelming glare that typically hinders observations of planets in closer orbits. This clarity has allowed astronomers to analyze its spectral properties, yielding insights into its atmospheric composition and thermal state. The spectral signatures indicate a cool, relatively low luminosity atmosphere compared to its inner counterparts, yet they also reveal hints of complex chemical interactions that might be driven by residual heat from formation or ongoing contraction. The mysterious nature of the Distant Wanderer is emphasized even more by the way it looks. Its known properties are hard to explain using normal models of evolution. Its mass is about the same as a giant planet's, and its radius is much bigger than usual for something so far away. Its low temperature and dim light suggest that it is slowly cooling down, which is common for small, isolated planets that aren't gaining much mass. Because of these things, it is a very important object for trying ideas about how planets form and change in places that are very different from the center of star systems. Because its orbit is wide and may be erratic, it has been through a lot of gravity changes over the years. It's possible that these interactions happened because it was close to other large bodies in its star cluster. This suggests that the system's early history was rough. These kinds of changes not only affect the planet's current path, but they may also change its structure and long-term security. Kepler 16b, Tatooine. Kepler 16b, which is often called Tatooine because it looks so much like the famous sci-fi world with two suns, is a great example of a circumbinary planet, which means it goes around not one but two stars that look like the Sun. Long-held beliefs that binary star systems were too unstable to support stable planetary paths were disproved when it was found. This part talks about the planet's physical features, how its orbit works, and the ideas about how it formed that make it an important example of the variety of planetary systems. Orbiting a pair of stars, Kepler 16b exists in a gravitationally complex environment where the competing forces of two stellar bodies challenge the traditional models of planet formation. Early theories suggested that the strong gravitational interactions in binary systems would either eject forming planets from the system or prevent their stable accumulation of material. Yet, this planet has maintained a remarkably stable orbit despite the perturbations inherent in such a dual star setup. Its trajectory around the binary pair follows a nearly circular path, providing strong evidence that planets can indeed achieve long-term stability even in what was once considered an inhospitable gravitational landscape. Based on measurements, its mass and radius are about the same as Saturn's. This puts it in the category of gas giants, though it formed in very different conditions than our solar system. The planet's mass and the makeup of its atmosphere show that it has kept a large gaseous envelope, even though its two host stars are pulling on it in different directions. Detailed chemical studies show that it contains traces of molecular hydrogen, helium, and maybe even other substances that help us understand how it formed. These findings are very important because they suggest that the formation process probably involved the slow buildup of gas from the circumbinary disk, rather than the sudden, catastrophic events that would be expected in a place with so much change. Kepler 16b's ability to show how planets move around in pair systems is one of its most remarkable features. Based on its current path, the planet either formed right where it is now, closer to the binary pair, or it formed farther away in a more stable part of the circumbinary disk, and later moved closer by interacting with the disk's material. In both cases, standard accretion models need to be re-evaluated because having two stars adds more heating, turbulence, and changes in the way things move that need to be taken into account. These things not only change the mass and makeup of the planet that is growing, but they also decide how the planetary system will be built in the end. Also, the fact that Kepler 16b exists brings up some interesting questions about whether or not circumbinary systems could support life. The planet is a gas giant and probably doesn't have life on it, but the fact that it stays in a stable orbit around a binary pair makes me think that smaller, hard planets could form and stay in similar conditions. This means that livable worlds are possible in more than just single-star systems like ours. Studying these kinds of planets could teach us a lot about the variety of planetary settings and how strong planet-forming processes are when the conditions around the star change. NGTS-4b, the Forbidden Planet. People often call NGTS-4b the Forbidden Planet because it lives in the hard Neptunian desert, which is a place around stars where strong stellar radiation should wipe out the atmospheres of planets the size of Neptune. This world stands out because, despite its harsh conditions, which usually cause its atmosphere to evaporate quickly, it still has a surprisingly thick and warm shell around it. Its ability to stay in such an unfriendly area goes against common ideas about how planets change over time and makes us rethink how atmospheres stay in place. At its center, this interesting sub-Neptune orbits its star far enough away that the high-energy flow should evaporate lighter gases. According to standard models, any planet in this orbital area should either lose all of its atmosphere or turn into a barren, rocky residue. On the other hand, observations show that this object has kept a large layer of gas undisturbed. It may be able to stay alive because of a careful balance between the planet's gravitational pull and the energy it takes in, as well as magnetic field effects that help keep some of the harmful star wind particles away. The transmission spectrum shows signs of water vapor and possible signs of other molecules, like carbon monoxide and methane. These results show that the atmosphere has kept its complex chemical makeup even though it has been exposed to radiation all the time. The discovery of these chemicals also makes us wonder about the planet's formation history. We wonder if it had an unusually strong envelope when it was first formed, or if later processes helped it get back some of the volatiles it lost. Its temperature has been measured to be still very high, even though it should be cooling quickly under such intense radiation. This means that heat inside the sphere, which could be caused by tides or heat left over from when it was formed, is very important for keeping the temperature balance of its atmosphere. In practice, it looks like the planet has come up with a good way to move heat around its surface, which lessens the damage that strong star radiation would normally do. On top of that, the planet's actual size is very interesting. Even though it is about the size of Neptune, its radius and mass are very different from those of similar exoplanets that live in safer places. Its puffiness comes from having a low density and a high atmospheric scale height, which goes against what you would expect from a world with so much strong energy. This strange state suggests that the planet's envelope is not only strong, but may also be going through ongoing processes that keep its air mass even though loss is supposed to happen. The planet moves along a pretty safe path, even though its environment is full of high-energy particles and strong radiation pressure. This stability could mean that the planet formed in a way that was stable enough to hold a lot of gas. It's possible that the planet moved to its current location after building up a thick atmosphere, or it formed nearby in conditions that let it do both. Either situation questions current ideas and creates new ways to learn about the variety of exoplanetary systems. HATP-11b. It's interesting to see how HATP-11b, an exoplanet about the size of Neptune, challenges predictions with its strange magnetic field and atmosphere. This planet goes against the usual ideas about planets with a middle mass because it has a strong magnetic field signature and water vapor has been found in its atmosphere. These findings suggest that the planet's history is shaped by a complex interaction between its own internal dynamics and outside forces. Observations have shown that this world's atmosphere is both complex and surprisingly rich in chemical components, even though it is smaller than gas giants. One of the most interesting things about the world is its magnetic field. HATP-11b has a magnetosphere that is surprisingly strong compared to other exoplanets of the same size. This magnetic shield is a very important part of keeping its atmosphere safe from the constant blasts of star winds and high-energy particles. In places where radiation can remove lighter gases, a strong magnetic field can help keep the atmosphere together by pushing charged particles away and slowing down the rate of erosion. The discovery of such a field goes against older ideas that said only bigger gas giants could keep up strong magnetic activity. Instead, HATP-11b shows that even smaller worlds like Neptune can make and keep strong magnetic fields. This is likely because they have strong dynamo processes going on inside them. Spectroscopic studies of the planet's atmosphere have given us more information. Water vapor in the near-infrared ranges shows that the atmosphere is rich and changing, with heavy molecules as well as hydrogen and helium. This finding is especially interesting because water vapor is a key molecule for figuring out how the atmospheres of other planets change chemically and thermally over time. Finding water vapor and other small molecules in the planet's atmosphere suggests that it may be going through complicated chemical processes that are affected by both starlight and heat from inside the planet. These results are very important because they show that planets with about the mass of Neptune can have atmospheres with a wide range of chemicals. This could affect how they change over time and whether or not any satellites that orbit them could support life. The way HATP-11b's orbit works adds to the story of its strange behavior. The planet is in a fairly close orbit around a moderately active star, so it is exposed to changing radiation from the star. This is likely what causes changes in the atmosphere's chemistry and temperature that happen with the seasons. These changing conditions could cause layers of clouds or dust that change over time, changing even more of the planet's qualities that we can see. Its atmosphere has changed over multiple transits, which has been carefully observed and gives us a glimpse into how extraterrestrial atmospheres change over time due to forces inside and outside the planet. The combination of a strong magnetic field, the presence of water vapor, and dynamic atmospheric processes makes HATP-11b a critical target for understanding how smaller exoplanets retain and evolve their atmospheres. Its characteristics challenge the simplistic view of Neptune-like planets as merely scaled-down versions of gas giants and open up discussions about the diversity of planetary magnetic and chemical processes. By studying HATP 11b in detail, astronomers can refine theoretical models of atmospheric retention and evolution, thereby expanding our understanding of how such worlds form and persist in harsh stellar environments. Wasp 127b, the Super Puff. With its very low mass and unusually wide atmosphere, Wasp 127b, also known as the Super Puff, goes against what is usually thought about how planets form. Even though this world is farther away than Jupiter, it has a very small mass compared to what you might expect. Its general makeup gives the impression of a space object that might be able to float on water, which is both an interesting and difficult idea for us to grasp when we think about how planets are put together. With its very low mass and unusually wide atmosphere, Wasp 127b, also known as the Super Puff, goes against what is usually thought about how planets form. Even though this world is farther away than Jupiter, it has a very small mass compared to what you might expect. Its general makeup gives the impression of a space object that might be able to float on water, which is both an interesting and difficult idea for us to grasp when we think about how planets are put together. Observations indicate the presence of elements like lithium and sodium in surprisingly high abundances. These chemical signatures are unexpected. Conventional models do not predict such enrichment for a planet with its mass and orbit. The detection of these elements suggests that Wasp 127b's atmosphere may be shaped by processes that are not yet fully understood. It could be the result of the accretion of material in a region with unusual elemental abundances, or might hint at past atmospheric escape events that selectively removed heavier elements, leaving behind a chemically distinct envelope. The thermal structure of the planet is of significant interest. The balance between the incoming stellar radiation and the cooling effects of its radiative processes seems finely tuned to allow an atmosphere that is both extended and stable over time. Detailed thermal measurements suggest that while the day side reaches extreme temperatures, the night side cools rapidly, creating strong temperature gradients. These gradients drive vigorous winds and complex circulation patterns within the atmosphere. The dynamic interplay between these opposing forces not only contributes to the planet's puffy appearance, but also influences the chemical stratification observed in its atmospheric layers. The physical features of Wasp 127b also make us wonder how it formed and how it evolved over time. Theories must explain either how it formed in an environment that was unusually high in gas compared to rocks, or how it lost a lot of material through the atmosphere, which changed its original makeup. Its current state could be a developmental stage where the planet is still losing matter to space, or it could be a long-term balanced state that is kept up by its star's constant energy flow. Both of these situations have huge effects on how we think about how physical systems change over time. HATP 67b, the shapeshifter. If Jupiter were a balloon, HATP 67b would be the one that is too big and shaking before it pops. In terms of size, HATP 67b is over twice as big as Jupiter, but only half as heavy. It is also so puffy that its gravity is barely holding on to its own atmosphere. It's not a world that lives, it just barely stays alive. Its density is extraordinarily low, among the lowest ever recorded. The numbers tell a story of paradox, big enough to block a measurable portion of starlight, but too light to be believable. It's like a planet-sized mirage, teetering on the edge of self-destruction. The planet's host star makes this even stranger. HATP 67 goes around a hot, rapidly spinning A-type star. These stars are known for blasting close objects with ultraviolet radiation and removing their atmospheres. In some way, though, HATP 67b still has a vibe. It ought to have been burned down to a hard core by now. Because the world is so big, it should be able to lose mass. It's still here, though. Its gravitational binding energy, the force holding the planet together, is so low that any serious solar flare could begin peeling it apart. It's likely in a state of active atmospheric escape, venting gases into space at a rate that threatens its long-term survival. If it loses enough mass, it could leave behind a dense metallic core. a planetary ghost like Towi 849b. So, what's keeping it puffed up? One candidate: ohmic heating. This is a process where charged particles in the atmosphere interact with magnetic fields, generating internal friction and heat. That heat may cause the planet to bloat, pushing its radius beyond what gravity alone should allow. It might be a planet being inflated from the inside out, an electrical balloon. Then there's the issue with the facts. When it was first seen, the planet's past depth seemed very small for being so big. Because it is not very dense, its shape is fuzzy, especially in some bands. Its atmosphere could get so big and thick with high-altitude haze that it actually makes things hard to see. Many tools may be wrong about how big this world really is because it is one of the few that can do that. And the distortion doesn't stop there. The planet may not even be fully spherical. Due to tidal forces from its close orbit, it could be stretched into an oblate or even egg-like shape. This would mean that some parts of the atmosphere are closer to the star than others, leading to uneven heating and mass loss. It might be bleeding gas in a lopsided leak. Also, the way it spins is a secret. Some models say it might not be tidally locked like a lot of hot Jupiters are. If this is true, it means that its rotation and orbit are not lined up correctly, which could cause interior turbulence and make the heat spread even less even. A gas cloud that spins and wobbles and can't find a stable balance. We may be seeing it at the end of its evolutionary arc. HATP 67b could be what a gas giant looks like just before it fails. Whether through loss of atmosphere, stellar disruption, or internal collapse, it may not last long, in cosmic terms anyway. This is not a young, thriving world. It's a planetary swan song. Even more interesting, it might not be by itself. Because HATP 67b has strange features like low gravity, high reflection, and skewed light curves, it's possible that other inflated gas giants are out there waiting to be found. They wouldn't show up like other planets do. They would be like ghosts in the system, hiding in the hazes, fake densities, and strange forms. So what is HATP 67b really? A gas giant too large for its own good? A balloon kept together by electric currents and magnetic stress? A prelude to atmospheric collapse? Maybe even the first of a hidden class of worlds we've only just begun to notice. Whatever it is, it's not stable, and it's not subtle. It is planetary fragility turned into a spectacle of scale. Wasp 18b, the Starbender. This world should be gone. Without a doubt, Wasp 18b is one of the closest gas giants ever found. It goes around its star in less than 23 hours. It goes around a hot F-type star so quickly that it should have passed through its host star a long time ago. Still, it hasn't. It's still there, living in a place where no big planet should be able to stay. It's caught in what should be a gravitational death spiral. Tidal forces from the star should be draining its orbital energy and pulling it inward. But instead of falling, Wasp 18b stays locked in place, like a marble hovering on the edge of a drain that never finishes flushing. The most likely reason, its star might not be playing by the rules. Unlike other stars of its type, Wasp 18 shows anomalously low magnetic activity. Without that magnetic drag, the star doesn't slow down its own rotation, and the planet's fall is delayed. The planet itself is a monster. At nearly 10 times the mass of Jupiter, it's one of the most massive gas giants ever detected in such a tight orbit. That bulk means it pulls hard on its star, potentially even distorting the star's shape through tidal deformation. Wasp 18b isn't just orbiting, it's pressuring its host from the outside, warping the very body that should be destroying it. The air there is also a puzzle. It is over 2,700 degrees Celsius on the day side of the planet, so scientists thought they would see clear signs of water vapor and other familiar molecules. They didn't find many, though. Some people think that heat and gravity have squished the atmosphere so much that water signs are hidden or washed away. Others think it might be going through chemical repression or active mass loss, changing into a version of itself that is heavier and more dangerous. That heat doesn't travel well either. Observations suggest Wasp 18b has an extreme day-night contrast with almost no circulation. The planet might be so tidally locked and thermally sealed that its night side remains dramatically cooler than its day side. The result is a world of extremes, blazing inferno facing its star, frigid dark locked in eternal night. Its orbit is being watched like a ticking time bomb. Over a decade of precision timing shows no significant decay, which stuns astrophysicists. By all current tidal models, the orbit should be shrinking. That it isn't means either the models are wrong or something even stranger is going on. Wasp 18b might be the exception that forces us to rethink planetary evolution near stars. There are also hints of violence from the past. The host star has an unusually high level of metals, which could be because it has eaten other worlds. It makes me think that Wasp 18b may have had brothers who are now very far away. If what they say is true, this planet is not just a survivor, it's the only one of its kind left in the system it came from. This planet is very big, very hot, very gravitationally stressed, has a strange atmosphere, and is very close to the edge of the universe. Everyone in this world is on the edge of extinction, and no one knows how much longer it can last. Ogle 2016 BLG 1190 LB, the Darkbound. It wasn't discovered in starlight, it was discovered in warped light, a flicker of distortion in a distant star's glow, bent by the mass of something invisible. That flicker became Ogle 2016 BLG 1190 LB, a planet-like object orbiting something we still haven't seen. Its host star might be a faint brown dwarf, or possibly something darker, something like a black hole. The object itself skirts the edge of planetary classification. With a mass of about 13.4 Jupiter masses, it rides the blurry boundary between supermassive planet and brown dwarf. Is it a planet? A failed star? A wandering object that got caught? No one agrees. But the fact that it was discovered at all is remarkable. Ogle 2016 BLG 1190 LB was detected through gravitational microlensing, a method that relies on the bending of light due to gravity, a prediction of Einstein's general relativity. As a distant background star passed behind the unseen system, the mass of the planet and its host temporarily distorted the star's light, like a magnifying lens flickering open and closed. From that one brief distortion, astronomers inferred the presence of a massive companion. That might not happen again. Microlensing doesn't let us stay in touch with Earth. You can't follow the light curve, study the spectrum, or watch the passage. The system is no longer aligned, and we might never see it again unless something else happens. Ogle 2016 BLG 1190 LB is a planetary ghost, because it was a short repeat in space-time that showed a secret world. Its orbit, if it even has one in the traditional sense, is massive. Calculations suggest a period that could span decades, depending on the host's mass. And here's where it gets stranger. The host object may not be a star at all. If it's a white dwarf or black hole, that would make Ogle 2016 BLG 1190 LB the first known planet orbiting a stellar remnant of that kind. Imagine a gas giant circling a point of darkness, a world bound to something that emits no light. It is located in the galaxy bulge, which is about 22,000 light-years away. Most exoplanets are found in the quiet area around the Sun, within a few thousand light-years of Earth. Ogle 2016 BLG 1190 LB, on the other hand, lives in the center of the Milky Way, where there are a lot of stars, and the gravitational pull is stronger. It was found using a method designed to find weak spots, and it might not be from there. Based on its mass, path, and host qualities, it may have formed somewhere else, like in the outer halo of a system that no longer exists, and been caught. Or maybe it drifted through outer space for a very long time before being caught by an unknown piece. It could be a world that went bad and got locked up, a person who survived a cosmic explosion. Not what we know about Ogle 2016 BLG 1190 LB that interests us, but how little we do know. Maybe it's a planet going around a host, we saw it once and might never see it again. Our definitions, categories, and even our ideas about what makes something a planet are called into question by this gravity shadow. If it turns out to be orbiting a black hole, it will be the first known case of a planet living around the dead body of a star. That changes everything. The result is that worlds can live on after stars die. The lack of light may hide many dark planetary systems in the galaxy, not because they are far away or too big. Kepler 70b, the resilient remnant. The ultra-short period planet Kepler 70b, which is sometimes called the resilient remnant, orbits a sub-dwarf B star and has gone through a lot of changes as its host star has evolved. This amazing world goes against common beliefs because it is in an orbit that should have become unstable during the star's powerful helium flash. Instead, it lives on as a mostly bare remnant, a rocky core that shows how extreme processes of planetary survival and return work. Formed in the tumultuous aftermath of its star's dramatic evolution, this planet now orbits at an astonishingly close distance, completing a full revolution in just a few hours. Its proximity subjects it to intense radiation and tidal forces, conditions that would typically lead to rapid disintegration. Yet, Kepler 70b remains intact, suggesting that it is a survivor of an evolutionary process that is as destructive as it is transformative. The prevailing theory is that the planet was once a gas giant or sub-Neptune, which lost its thick gaseous envelope during the host star's dramatic transition from a red giant to a sub-dwarf B. What remains is a dense, rocky core that offers a rare glimpse of the inner structure of a planet that has been stripped of its volatiles. Its high density and small radius, relative to its mass, imply a composition rich in heavy elements, predominantly iron and silicates. This composition indicates that the planet's original envelope was removed, likely by a combination of intense stellar winds and tidal stripping during the star's helium flash phase. The resulting remnant is essentially the bare core, preserved by the harsh conditions that would have otherwise obliterated a less robust structure. In essence, this planet is a living fossil, a testament to the resilience of planetary cores in the face of catastrophic atmospheric loss. Despite the difficulties caused by the bright host star and the short orbital period, data show absorption patterns that are consistent with a mostly rocky surface. The fact that Kepler 70b doesn't have any strong volatile signals supports the idea that it is all that's left of a much bigger planet. Its mass and density have been limited by a close study of its transit light curves and radial velocity readings. This supports the idea that we are looking at a stripped core instead of a normal terrestrial planet. The way orbits work is very important for keeping this world alive. Its orbit is very close to the Moon, so it is exposed to huge tidal forces that helped it lose its atmosphere and are still affecting its present state. These forces could cause a lot of warmth inside, which could lead to ongoing volcanic activity that could even help the temporary atmosphere get filled up again and again. The constant interaction between the planet's tides and its internal structure makes it possible to study how very strong gravity fields can change how planetary bodies form and change over time. HIP 65426b, the distant outlier. HIP 65426b, also called the distant outlier, is a young, very large exoplanet that has been directly photographed a very long way from its star. Its presence goes against common ideas about how stars and planets form, because it is found in a place where normal core accretion processes have trouble explaining how such a huge object could have formed. This planet is far from its star's strong radiation and gravitational pull, and it gives us an interesting look into a different way that planets form, one that might involve disk instability or even processes that are similar to how brown dwarfs form. At a projected separation of several hundred astronomical units, HIP 65426b exists in an environment that is radically different from the compact, high-density regions where most planets are found. This vast distance from its star means that it has experienced relatively little stellar interference since its formation, preserving its youthful characteristics. Observations reveal that its atmosphere is still glowing with residual heat from its birth, which in turn provides clues about its age and internal structure. The thermal emission from this planet has been captured in multiple infrared wavelengths, allowing astronomers to model its temperature profile and infer the presence of molecules that are typically found in young, warm gas giants. The story is made even more complicated by the planet's mass, which is thought to be several times that of Jupiter. According to the traditional core accretion theory, it should be very difficult for such a huge planet to form so far away, because there isn't much matter in the outer parts of the protoplanetary disk. Instead, the discovery of HIP 65426b suggests that there are other ways that galaxies could have formed, such as gravitational instability, in which a part of the disk falls apart quickly and a gas giant is formed. Even though this process isn't well known, it might explain why the planet has a large mass and is able to keep its thick, wide atmosphere even though it is in a faraway orbit. The observed spectral lines indicate the presence of common molecules, such as water vapor and carbon monoxide, along with hints of more exotic species that could be the result of high-temperature chemistry in a young, dynamic atmosphere. These measurements not only refine our understanding of the planet's physical properties, but also serve as a critical test for models of planetary atmospheres in extreme environments. The chemical signatures seen in the data have prompted researchers to revisit assumptions about the opacity, thermal structure, and energy transport in the atmospheres of gas giants formed by disk instability. Furthermore, the planet's strange path has important effects on the way its home system works. Its large distance from its parent star suggests that it may have moved after it was formed, or it may have formed in a very different environment than most alien systems. This orbital arrangement brings up important questions about how stable these kinds of systems are over time, and how other, maybe still undiscovered partners might affect them. At these distances, the interaction of gravity forces can cause complex orbital resonances. This makes HIP 65426b an interesting object to study in terms of dynamics. GJ 3512b, the giant defier. GJ 3512b, also called the giant defier, is an amazing world that orbits a low-mass red dwarf star. It is thought that huge gas giants shouldn't form around these kinds of stars very often. Still, here it is, going against our accepted models because it lives in a system where planet-forming materials are thought to be scarce. Core accretion theory says that low-mass stars don't have the building blocks needed to make big planets, but this planet's existence goes against that theory. This new planet, GJ 3512b, seems to have formed through different methods that allow gas to build up quickly. This has made scientists rethink how planets form around small stars. From the moment GJ 3512b was discovered, its mass and size immediately stood out. Despite orbiting a star with a fraction of the Sun's mass, this exoplanet is several times more massive than Jupiter, placing it at the extreme end of the planetary mass distribution for red dwarf systems. The conventional core accretion model would predict that a star of such low mass would be unable to produce a core robust enough to accrete such a large envelope of hydrogen and helium. Instead, the existence of this giant suggests that disk instability, a process where regions of a protoplanetary disk rapidly collapse under their own gravity, may play a more significant role than previously believed in these environments. Such a process could lead to the formation of a massive planet before the disk disperses, bypassing the slower core growth that typically limits planet size around low-mass stars. Detailed observations have revealed that GJ 3512b's atmosphere exhibits characteristics that hint at its unusual formation history. Spectroscopic data show absorption features from various molecular species, suggesting that the planet's atmosphere, while similar in some ways to those of gas giants around Sun-like stars, may also possess distinct chemical signatures influenced by its unique birth environment. The high-pressure, high-temperature conditions during its formation likely contributed to a chemical composition that differs markedly from that of giants formed around more massive stars. This unique atmospheric makeup is critical for testing and refining models of planetary formation in systems that were once considered incapable of producing such enormous planets. The way its orbit works is more proof of how defiant it is. GJ 3512b's path isn't a perfect circle. This could be because of past gravity interactions, or even the effect of other bodies in the system that haven't been found yet. The irregular orbital shape of this planet goes against the idea that planets around low-mass stars should settle into smooth spherical orbits. It also suggests that the planet may have formed through a turbulent history of dynamical interactions. The planet's gravitational pull on its surroundings and the chance that it could move around in its orbit give us new ways to look at how huge planets change over time in these strange places. KOI 1843.03 Planet of the Apes. KOI-1843.03, which is sometimes called Planet of the Apes because of how badly its form changes when the tides are high, is a very difficult object for us to understand in terms of orbital stability and planetary structure. This world has an extremely short orbital period. It goes around its star in just over 4 hours, which is so close that the planet is constantly pulled toward its star, stretching it out. Conventional planetary models have long said that such strong tidal pressures would quickly tear a planet apart, but it's still happening here. This shows how well stellar bodies can adapt to harsh conditions. At the heart of its mystery is the strong pull of gravity from its star. The tidal forces acting on KOI 1843.03 are not only strong, but they can also bend its whole structure in an orbit that lasts only hours. Observations show that these forces stretch the planet into a very long, almost needle-like shape, which doesn't seem to work with the planet's own gravity, which would normally keep it round. Because it is so close to its star, it is in a constant tug-of-war where the star's gravity pulls it in and pulls it out every second. This dynamic equilibrium, if you can call it that, points to internal processes that fight the disruptive forces and keep the planet whole even though it is about to be destroyed. Even though KOI 1843.03 has been severely deformed by tides, its density suggests that it is mostly made up of rocks with a structure that is full of heavy elements. If a planet is under so much stress, you would think it would lose a lot of its material, or at least mix its lighter elements in a strange way. This high density is a surprise. Instead, studies show that its core is still surprisingly compact. This suggests that the processes of differentiation, which are when a planet splits into layers of different makeup, may have worked very well. In a world where gravity and tides fight every minute, this kind of unity is necessary to stay alive. The planet's ultra-short period also provides an unprecedented natural laboratory for studying extreme planetary dynamics. Its rapid orbit means that its day-night cycle is virtually non-existent in the conventional sense. The planet is bathed in near-constant stellar irradiation, leading to severe temperature gradients across its surface. This extreme thermal environment likely drives vigorous internal currents, which in turn could contribute to the planet's ability to redistribute energy and resist total disintegration. The delicate balance between tidal distortion, thermal expansion, and internal gravitational cohesion presents a unique case study that challenges the limits of our current models. KOI 1843.03 makes us think about what such harsh environments mean for the development of the world. Its presence shows that planets can form and stay around in situations that were once thought to be impossible. Long-lasting, stable shape for billions of years, or at least for a big part of its life. This planet's ability to stay in this shape shows that the ways planets form and stay alive are much more varied and flexible than was thought before. HD 189733b, the Glass Storm Giant. HD 189733b is a great example of a very hot Jupiter whose weather conditions are so extreme that they don't fit with most weather models. It gets so hot on this world that its atmosphere is full of strange things happening all the time. For example, silicate compounds can turn into glass-like raindrops, and winds can reach speeds you can't even imagine. Observations show that the side facing the Sun has temperatures higher than 1,200 degrees Celsius, 2,190 degrees Fahrenheit, which is caused by a dynamic interaction between strong solar radiation and fast air circulation. Because it is so hot, the environment is unstable, and the top layers of the atmosphere are always moving. At these very high temperatures, ordinary substances like silicates don't stay solid or liquid like they normally do. Instead, they change into strange condensates. For example, high-resolution spectroscopic readings have shown that there are absorption patterns that are consistent with silicate clouds. This means that the rock that has been vaporized may cool and collect into droplets like glass rain. This event not only makes us think about how chemicals work in the atmospheres of planets, but it also gives us a striking picture of a world where glass showers might fall from a sky that is otherwise rough. In addition to its strange rain, HD 189733b has strong winds that can reach over 7,000 km per h. The huge differences in temperature between the planet's day and night sides cause these very fast air currents. Because one side is always hit by hot stellar radiation and the other is thrown into darkness, there is a strong difference in temperature that causes energy to be redistributed. Because of this, jet streams and super-rotating winds are created, which hit the Earth hard and keep the atmosphere turbulent all the time. The wind speeds not only show how much energy is in the system, but they also mix the layers of the atmosphere, which changes how the glass-like particles are spread out and how they form. The dynamics of such a harsh environment force astronomers to revisit conventional theories of atmospheric physics. Standard models predict that close-in gas giants should experience significant mass loss due to hydrodynamic escape driven by stellar irradiation, yet HD 189733b retains a thick, complex envelope. Its weather systems, shaped by rapid rotation and strong tidal forces, illustrate how heat transport and momentum exchange operate on scales far beyond anything observed in our solar system. The interplay between radiative heating, chemical condensation, and aerodynamic forces generates a highly structured atmosphere with distinct layers that vary in composition, temperature, and pressure. The things we can see about HD 189733b have big effects on how we think about the atmospheres of other planets. Finding silicate raindrops that look like glass gives scientists a chance to study how refractory materials condense in very hot conditions, which could help them figure out what might happen on other hot Jupiters. These results also make us wonder about how these planets change over time. Being exposed to strong radiation all the time and the changes that happen in their atmospheres could change their makeup and even their mass over very long periods of time. Tess Py C, the Resonant Wanderer. Discovered by Tess, this is Py C, a planet whose orbital pattern goes against what is expected because it lives in balance with a faraway super-Jupiter. Even though it's not very big, this super-Earth has features that make standard ideas about how planetary systems are put together hard to understand. Observations show that it goes around its star at a distance that puts it in a complicated gravity dance with a bigger object. It was a surprise that the planet existed in such a delicate resonance, because models used to say that the disturbances from a huge neighbor would make it impossible for smaller inner worlds to stay stable over time. According to very accurate transit and radial velocity readings, the planet's orbit is very circular. However, because it is so close to its giant counterpart, there is a slight tug-of-war between their gravity pools. This dynamic interaction changes not only its orbital period, but also its internal structure and the way its atmosphere changes over time. The interaction between starlight and gravitational resonance seems to keep this planet's climate pretty mild, at least compared to other nearby worlds that have to deal with very hot conditions. Spectroscopic measurements suggest that the atmosphere may contain volatile chemicals, possibly including small amounts of water vapor. However, because the environment is so high energy, any atmospheric holding must be carefully balanced by processes that are constantly recharging and escaping. Core accretion models that are commonly used say that smaller planets should have a hard time gaining enough mass or keeping their atmospheres in places where they are surrounded by large planets. However, this item not only made a space in the system, but it also made it safe. It is thought that the planet may have started out farther away, in a cooler, more secure area for protoplanetary disks, and then moved closer to the Sun. This trip inward would have been slowed down by the larger companion's gravitational pull, and it would have finally settled into an orbit where resonance protects it from disruptive forces. The system's harmonic dynamics have big effects on how the planet's temperature and chemistry change over time. Interactions between tides, for example, can heat up the inside of the rock, which may cause natural activity on the surface. Volcanic outgassing could happen as a result of this kind of activity, adding more molecules to the atmosphere, and maybe even making places where temperatures and pressures are very different from the world normal. The planet's current state is the result of a long history of migration, gravity shaping, and atmospheric development. This interaction of internal and external forces makes for a complicated picture. The system's orbital design makes us question what we thought we knew about how multiple planets interact. The stability seen here shows that resonant orbits can be a long-term answer that lets different types of planets live together, even in systems where the masses of the planets in the system are very different from each other. The gravitational forces between the worlds are very carefully balanced, as shown by detailed models. Any big change could cause orbital chaos or even ejection from the system. This delicate balance is a warning that how planets grow and stay alive can depend on cosmic luck just as much as they depend on physical laws. 2. M1207b, the bridge object. 2M1207b is an interesting case of a partner star with the mass of a planet that blurs the lines between planets and brown dwarfs. This object, which is orbiting a young brown dwarf, makes us question how stars and planets form because it lives in a place between planets and substellar objects, where its mass and physical properties are similar to those of both. It was found using direct imaging, but its low brightness and cool temperature suggest that it is in a unique place in the mass spectrum. This means that it may be a transitional stage in the formation of heavenly bodies. In this system, the host is a relatively low-mass brown dwarf, an object that itself sits on the border between the smallest stars and the largest planets. The companion, 2M1207b, has a mass that is only a few times that of Jupiter, yet its physical properties hint at complexities more often associated with more massive objects. Its atmospheric composition, for instance, exhibits spectral features that are unexpected for an object of its kind. Observations in the infrared revealed the presence of water vapor and carbon monoxide, along with hints of methane. These chemical signatures suggest that even at such low masses, the processes of cloud formation and chemical equilibrium are rich and varied, challenging our understanding of how atmospheric constituents are retained or depleted in low-gravity environments. There is a lot of disagreement about how 2M1207b came to be. Because there isn't a lot of material in the protoplanetary disk around a substellar host, traditional core accretion models have a hard time explaining how these kinds of things can orbit brown dwarfs. Because of this, scientists are looking into other ways it might work, like gravitational instability, in which parts of the disk quickly fall apart under their own gravity to form things with planetary-level masses. If 2M1207b formed in this way, it could tell us a lot about the conditions that are needed for planets to form around brown dwarfs or very low-mass stars. Its orbit, which is pretty far away from its mother, also suggests that it may not have formed in one place, but rather through dynamic interactions that sent it to where it is now. According to the data, the object has a cooler temperature than most hot Jupiters, but it has a surprisingly wide range of molecules. The mix of water, methane, and carbon monoxide in the atmosphere shows that its processes are affected by both the heat left over from formation and chemical reactions going on outside that are being sped up by radiation. The general brightness is low, but the spectral lines that were seen are deep and well defined. This suggests that there may not be many high-altitude clouds in the atmosphere, or that the clouds are made up of particles that don't cover up the molecular features as much as was thought. This clarity gives us a rare look into how the atmospheres of these borderline objects change over time, closing the gap between normal planets and brown dwarfs. Thermal evolution of 2M1207b adds complexity to its characterization. As a young object, it still retains significant heat from its formation, which is radiated away over time. This residual thermal energy affects its atmospheric scale height and influences the overall spectral energy distribution. Models of its cooling history suggest that it might transition through various phases, initially appearing more like a traditional gas giant and gradually evolving into a cooler, more methane-rich atmosphere as it ages. Such a transition, if observed over time or compared with similar objects, can serve as a benchmark for understanding the evolutionary trajectories of substellar objects. The study of 2M1207b is very important for helping us figure out what makes a planet different from a brown dwarf. Because of its special features, we need to rethink the strict mass boundaries and formation scenarios that have usually kept these groups separate. In doing so, it brings up the idea that nature might not fit neatly into our neat categories. Kepler 444, the ancient system. Kepler 444, also called the ancient system, gives us a unique look into the early days of planet formation. This small system of 5 worlds, each about the size of Earth, orbits an 11 billion-year-old star. It questions our ideas about how planets form in places that aren't very rich in metals. Even though the star is very old, these rocky partners formed when the galaxy was still young. This is direct proof that small, terrestrial worlds can form even in very different conditions than those we live in now. Observations show that over billions of years, these small planets have kept their orbits surprisingly fixed. The fact that they are orbiting such an old home makes us rethink how long it takes for planets to form and stay alive. In particular, the star's low metallicity suggests that the protoplanetary disk from which these worlds formed wasn't very rich in heavy elements. This is very different from the settings that helped our own solar system's planets form, which were much more rich. Still, these bodies were able to gather enough matter to form solid, rocky centers. This suggests that accretion processes might work better than thought in places with low metallicity. Frequency domain studies of the star and its planets have given us important information about the system's chemical makeup and how it formed. The host star's absorption lines show that it lacks elements like iron and silicon compared to younger stars. On the other hand, the planet's densities show that they are mostly made of rocks. This finding is interesting because it suggests that nature can build stable, grounded worlds, even when there aren't many building blocks available. The fact that these planets have been around for more than 11 billion years shows that the processes of losing atmospheres and rocks changing over very long periods of time, the way the orbits of this very old system move, is also very interesting. According to detailed transit studies, the planets move in nearly circular orbits with little variation. This suggests that the system has been stable for a long time. This stability may have been reached through a slow movement process within a disk that was mostly still. This let the world settle into a peaceful arrangement that lasted through the galaxy's rough early history. This stability not only helps models of how planets move, but it also brings up interesting questions about the possibility of habitability in old systems, where life, if it ever did exist, would have developed over a lot longer periods of time than on Earth. HATP-26b, the warm Neptune. The atmosphere of HATP-26b, which is sometimes called the warm Neptune, is surprisingly full of metals, which goes against what most people think. Unlike most worlds like Neptune, this one has a chemical makeup that makes core accretion models less accurate. This suggests that it formed in a way that is different from that of gas giants and smaller ice giants. Orbiting a relatively sun-like star at a moderate distance, this planet experiences milder stellar irradiation compared to the blistering environments of hot Jupiters. Yet its atmosphere reveals a surprising abundance of heavy elements. Detailed spectroscopic analysis has detected elevated levels of metals, elements such as oxygen, nitrogen, and even traces of heavier species, which contrasts sharply with the expected composition of similar-sized exoplanets. Such findings suggest that during its formation, the planet may have accreted more solid material than typical for its class, or that subsequent processes enriched its envelope with heavy elements. The chemical clues found in the atmosphere are very important for figuring out how the planet evolved. Through measuring absorption lines in the infrared and visible spectra during transits, scientists have found that the atmosphere is not only long, but also has a lot of different chemicals. These readings suggest that the planet went through a lot of mixing, which could have been caused by strong air circulation or even leftover heat from when it was formed. This kind of mixing could bring heavy elements from the inside out, which is what caused the metal increase that was seen. The thermal structure of this warm world tells us a lot about how its energy is balanced. Even though it gets some energy from stars, the atmosphere of this planet has a temperature difference that creates strong winds and circulation patterns. These changing processes help move heat from the day side to the night side. This keeps temperature differences from being too big, which could cause the atmosphere to break or run away. Models that take these things into account suggest that the planet's stability is a fragile balance between atmospheric cooling and interior heat, with heavy elements changing the planet's opacity to keep the balance. The planet has been able to avoid the more violent interactions that closer gas giants have had because its orbit is almost spherical and it is not too close to its home star. On the contrary, it seems to have formed in a relatively calm area of the protoplanetary disk where rocks and gas gathered more slowly. This soft formation setting might explain both why there was a large atmosphere and why there was an enrichment of metals. This is because the slower accretion process made it easier for heavy elements to mix. PDS-70b, the forming giant. A unique look into the birth of a gas giant is given by PDS-70b, also known as the forming giant. This young exoplanet, which was photographed directly in the gap of its mother star's protoplanetary disk, is one of the first clear examples of a big planet that is still forming. Its finding has changed the way we think about how planets form from the swirling clouds of gas and dust that circle new stars. Embedded within a gap carved out by its own formation processes, this world is actively accreting material from the surrounding disk. High-resolution imaging has revealed luminous structures around the planet, indicative of a circumplanetary disk where moons might eventually form. This observational breakthrough confirms that giant planets can form by accumulating substantial amounts of gas while still interacting with their natal environments, a process that was largely theoretical until recently. There is water vapor, carbon monoxide, and other chemicals that are common in atmospheres that are still young and changing. Based on these readings, it seems likely that the planet is still giving off a lot of heat from when it was formed, which is adding to its swollen, long shell. Multiple infrared wavelengths of the planet's thermal emission have been used by scientists to make accurate temperature maps that help them build models of how planets grow and shrink. One of the most interesting things about PDS-70b is that it tests ideas about how disks and planets interact. The young giant's gravity has not only filled in a hole in the disk, but it has also made spiral shapes in the material around it. These traits directly show how the planet and its birth surroundings changed over time. They also give us hints about how these changes affect the final mass and orbital properties of giant planets. The ongoing build-up and shock heating also give us clues about how well gas is being captured and how the planet will eventually settle into a stable shape. Understanding how planetary systems form is affected by the study of PDS-70b in a wider sense. It can be used as a natural laboratory to study how young planets interact with their surroundings, how they control their mass growth, and how disk loss and planet movement change the structure of new systems as they form. Astronomers can improve models of core accretion, disk instability, and the timescales over which these processes happen by comparing PDS-70b to other growing giants. Wolf 503b, the resilient sub-Neptune. With its interesting mix of traits, Wolf 503b questions the traditional binary way of classifying planets. This planet orbits an old star that doesn't follow the rules by having short orbital periods and showing signs of being partly made of rocks. This makes it hard to label exactly as either a gas planet or a rocky planet. This world has been seen to have a thick layer of gas around it, but its general density is higher than what you might expect for a normal sub-Neptune. It might be a transitional object, a mix of a mini-Neptune and a super-Earth based on its features. Astronomers have been able to get a pretty good idea of its mass and diameter by using high-precision transit photometry and radial velocity readings. These numbers show that even though it is very big, the mass density is much higher than what would be expected for a planet with a thick atmosphere. One main theory is that Wolf 503b formed in a place with a lot of heavy elements. This could be because of the special makeup of the protoplanetary disk around its mother star. In this case, the planet might have been able to form a huge rocky core that later surrounded by a thin layer of gas. On the other hand, it could have lost some of its lighter parts to the atmosphere over time, leaving behind a heavier relic. Early results suggest the presence of water vapor and other volatile compounds, yet with indications that heavier elements contribute more significantly to the overall makeup than is typical in similar sub-Neptune worlds. These findings support the idea that the planet's evolution involved substantial mixing or partial stripping, processes that may have enhanced its metallicity. In turn, the elevated metallicity could have contributed to a higher mean molecular weight for the atmosphere, reinforcing the observed high density. Residing in a compact system, its short orbital period implies that it endures intense stellar irradiation. This constant bombardment of high-energy photons can lead to complex atmospheric dynamics, driving vigorous winds and possibly even partial atmospheric erosion. Yet, despite these harsh conditions, Wolf 503b remains surprisingly stable, a fact that underscores its resilience. The interplay between gravitational retention and radiation-driven escape in this environment makes it an excellent candidate for refining theoretical models of atmospheric evolution. It's also possible that Wolf 503b is part of a range of possible results for planets that go beyond the clear limits of existing classification systems. Its features show that the processes that control planet formation and atmospheric preservation could lead to a range of results, from strong, rocky worlds to gas giants with a lot of gas inside them. NGTS-1b, the M-dwarf giant. According to normal models, NGTS-1b is a very rare case of a planet forming in a way that doesn't fit with how planets usually form. It is a giant planet orbiting a low-mass M-dwarf star. Even though there isn't much matter around small stars, NGTS-1b has built up a mass about the same as Jupiter. According to the usual core accretion process, red dwarfs can't make planets that big, but this object's presence goes against that idea. NGTS-1b is definitely a Jupiter-massed giant, as confirmed by many years of observations using transit photometry and radial velocity readings. Even though it is close to its host star, its orbit is stable, which is strange because core accretion models say that low-mass stars shouldn't be able to gather enough solid matter to start runaway gas accretion. Instead, NGTS-1b seems to have formed through a different route. One possible reason is disk instability, which happens when a piece of the protoplanetary disk quickly falls apart under its own weight to create a huge planet without having to slowly form a stable core. Even though this method isn't very good in many situations, it might become the main one in places where the disk is very heavy compared to the star. NGTS-1b's atmospheric properties also provide intriguing clues about its formation and evolution. Spectroscopic observations reveal an atmosphere that, while sharing similarities with those of gas giants around more massive stars, also exhibits subtle differences. The chemical composition appears to be influenced by the host star's low metallicity and the overall scarcity of heavy elements in its environment. For instance, the abundance of molecular hydrogen is typical, yet there may be a lower relative concentration of heavier molecules. These findings suggest that the planet's atmosphere may be less enriched in metals than its counterparts orbiting higher mass stars, offering a natural laboratory for testing the influence of stellar environment on planetary chemistry. Researchers have found that NGTS-1b is exposed to a lot of radiation from its mother star. However, the amounts are not as strong as they are around stars like the Sun. This balance creates a climate that is warm and stable, with a temperature structure that lets air flow quickly. The planet's atmosphere is controlled by small differences in temperature between day and night, which help keep the surface of the planet fairly warm. Finding and describing NGTS-1b has huge effects on how we think about the population of other planets. The fact that it exists shows that even M-dwarf systems, which make up most of the stars in our galaxy, can make gas giants. This goes against what most people think and opens up the number of different solar system structures. It also gives important observational limits that can be used to improve models of disk instability and core accretion in low-mass settings. This helps us understand the different ways planets can form. Kepler 1647b, the binary beacon. Kepler 1647b, which is sometimes called the binary beacon, is a beautiful example of a planet that does very well in the complicated gravity environment of a system of two stars. This gas giant goes around two stars that are like the Sun. This goes against long-held beliefs that binary systems are too unstable to support stable planetary orbits. Transit photometry and accurate measures of radial velocity have shown that this world stays in a stable orbit around both of its hosts. Even though two stars are pulling on the planet, its orbit stays incredibly round. This is because of the delicate dynamical balance that controls its motion. Models show that the planet might be stable if it formed in a circumbinary disk, which is where matter is spread out around both stars instead of just one main star. This model for how the planet formed suggests that its growth was controlled by very different rules than those found in more common single-star systems. As a gas giant with a mass and radius comparable to Jupiter, its envelope exhibits chemical signatures typical of hydrogen and helium, yet it is also influenced by the dual stellar irradiation from its two suns. The combined radiation from both stars creates unique heating patterns on the planet's surface, which in turn affects atmospheric circulation. High-resolution spectroscopic observations indicate the presence of trace molecules that hint at ongoing chemical reactions driven by this unusual radiation environment. The thermal structure appears to be more complex than that of gas giants orbiting single stars, with potential variations in temperature and pressure across different regions of the atmosphere. Simulations suggest that gravitational interactions within the circumbinary disk played a crucial role in sculpting its orbit, potentially leading to inward migration and eventual stabilization in a resonance with the binary pair. Such resonant configurations not only help maintain orbital stability, but may also influence the accretion processes that determine the planet's final mass and composition. The delicate interplay of gravitational forces in such systems provides a natural laboratory for testing and refining theoretical models of planetary migration and disk dynamics. Kepler 1647b's presence also calls into question the idea that paired star systems are naturally not good for planet formation. Its steady, long-lasting path around the Sun shows that nature can keep things in balance so that big planets can form and stay in place even when there are big changes in gravity. K218b, the habitable mini-Neptune. K218b is an interesting world that is hard to put into a single category because it is kind of like a mix between a mini-Neptune and an exoplanet that might be livable. This planet, which orbits in the temperate zone of its red dwarf home, has gotten a lot of attention for having a fairly mild average temperature, even though it has a thick, long-extending envelope of hydrogen and helium around it. The planet's existence goes against common beliefs that say strong radiation from low-mass stars would remove flammable substances from small things that are close to the star. Instead, K218b still has a thick atmosphere, and scientists have even found signs of water vapor in its spectrum. Using transit spectroscopy, scientists have found absorption patterns that suggest water may be present. This is a surprise finding because mini-Neptunes are usually very unstable. People are arguing about whether K218b might have conditions that are good for life, or at least complex air chemistry, even though its surface is still covered by a thick layer. Now researchers have to figure out how such a thick atmosphere can stay in a place where the action of the host star would normally wash away a lot of the atmosphere. The planet's mass and radius imply a low overall density, a property that points to an envelope inflated by stellar heating as well as possible internal heat sources. Models indicate that the balance between radiative cooling and heating from both stellar irradiation and residual formation energy plays a critical role in maintaining its swollen state. Furthermore, the relatively benign radiation environment of its M-dwarf host, compared to hotter stars, could allow the atmosphere to remain stable over billions of years. This stability, in turn, opens up new questions about the potential for atmospheric retention in planets that straddle the line between rocky super-Earths and gas-dominated mini-Neptunes. K218b may have gone through a lot of movement during its evolutionary past. If it had formed farther out in a cooler part of the protoplanetary disk, it might have had time to build up a thick layer of gas before moving into the livable zone. A path like this would go against the usual core accretion models and show that migration processes are more effective than was thought before. This is especially true in low-mass star systems, where disks tend to last a long time and be chaotic. More in-depth computer studies are now being used to model these processes and see how the opposing forces of atmospheric escape and restocking can be balanced. Spectroscopic research keeps helping us get a better idea of what K218b's atmosphere is made of. Recent observations have found chemical features that point to the presence of other substances, maybe even biosignature gases, but the data are still not clear. Ongoing studies with next-generation telescopes should help us figure out these details even better, which could change how we think about mini-Neptune atmospheres in livable zones. Epic 2 20504338b, the ultra-short sub-Earth. Epic 2 20504338b is an interesting new ultra-short period planet. It is a world about the size of Earth that goes around its star in less than a day. It's even more amazing that it exists because theory models say that any rocky planet in such a close orbit should lose its atmosphere very quickly, or even be thrown off course by the tides. However, this planet has survived, giving us a rare look into how small, close-by worlds stay alive. The planet's size, mass, and extremely short orbital period imply a density that challenges standard assumptions about rocky exoplanets. Its proximity to its host star exposes it to an intense flux of stellar radiation and gravitational forces, conditions that would typically vaporize volatile compounds and erode the surface over time. Despite these hostile conditions, EPIC 220504338b appears to have maintained a compact rocky structure, suggesting that its composition may be dominated by refractory materials that can withstand extreme temperatures. Astronomers have been able to tightly limit its mass and radius by using transit photometry and radial velocity data to make observations. Based on these predictions of density, it looks like this planet doesn't have a big atmosphere. Instead, it has a mostly rocky core. Since there isn't a thick envelope, it means that air escape has been very effective in this setting, getting rid of any volatile chemicals that may have been there before. Because of strong tidal forces and high-energy radiation, this process can be used as a natural laboratory to study how far air erosion can go on nearby exoplanets. The formation of EPIC 220504338b brings up important questions. It is generally thought that planets that form so close to their stars would either never be able to get an atmosphere or would lose it very quickly if they did. It's possible that this planet formed farther out in the system and then moved in, losing its atmosphere as it got closer to the star's core. It could have also formed on its own, in a place with very high density, which would have made it easier for heavy elements to form quickly over lighter gases. Spectroscopic studies of the planet's transmission spectrum have so far revealed minimal signs of an extended atmosphere, reinforcing the view that it is a bare, high-density world. The spectral features that are detectable are consistent with silicate materials and iron-rich compounds, common in rocky bodies that have undergone differentiation. These observations contribute to a growing body of evidence, suggesting that ultra-short period planets can exist as stripped cores, offering crucial insights into the processes of atmospheric loss and the ultimate fate of rocky planets in extreme environments. Wasp 121b, the disintegrating hot Jupiter. Wasp 121b is a striking example of a hot Jupiter whose atmosphere is about to break apart. This planet is very close to its host star, which is very dangerous, and its atmosphere is showing signs of being unstable and changing quickly. This is not what normal models would expect for long-term stability. Its crazy behavior has given it the name the disintegrating hot Jupiter, which shows how the changing conditions that threaten its survival make it stand out. From what scientists have seen, Wasp 121b's atmosphere is getting longer and thinner because of the strong radiation it gets from stars. The star's high-energy photons heat the outer layers of the atmosphere to very high temperatures, which makes them expand and finally escape into space. A broad, comet-like tail seen following the planet shows that it is losing mass. This tail is a clear sign of the ongoing erosion of the atmosphere. The planet's mass and radius show that it has a low density, which is typical of hot Jupiters. However, its orbital distance puts it in a zone where tidal forces and star irradiation are very strong. All of these things work together to make the world in a tricky situation between keeping the atmosphere and letting it leave. High-resolution spectroscopic readings show that the atmosphere is made up of charged metals and molecular species that are going through fast chemical changes. This makes the picture of how the atmosphere moves even more complicated. The way its path changes over time is one of the most interesting things about Wasp 121b. Due to its very close orbit, the planet is subject to strong tidal forces that not only cause it to lose atmosphere, but also slowly change its path over time. Models say that Wasp 121b may finally spin inward and be sucked up by its host star. This would be a dramatic ending that would show us what happens to gas giants that are getting close. This coming death makes us think about how long these kinds of planets can live and how they might change over time if they become hot Jupiters. The chemical composition of Wasp 121b's atmosphere is a subject of intense study. Spectroscopic observations during transits have identified unusual absorption features, including those corresponding to water vapor, carbon monoxide, and ionized metals like iron and titanium. These features suggest that the planet's atmosphere is in a state of dynamic equilibrium, where the competing processes of thermal expansion, chemical dissociation, and hydrodynamic escape are constantly at work. The detection of such exotic species at high temperatures pushes the limits of our current atmospheric models and underscores the need for new theories that can accommodate the extreme conditions found on disintegrating hot Jupiters. HD 219134b, the Rocky Beacon. HD 219134b is a close super-Earth that goes against what most people think because it is very dense and mostly made up of rocks. This planet stands out because it seems to have kept its compact, solid structure despite the strong radiation it gets from a bright, relatively quiet star. HD 219134b, also known as the Rocky Beacon, is a key object for studying how terrestrial planets can form and live in places that are very unstable for rocky bodies. High-precision measurements of its mass and radius reveal a density that is significantly higher than what would be expected if the planet had retained even a thin gaseous envelope. This strongly suggests that HD 219134b is composed primarily of heavy elements such as iron and silicates. The planet's layered internal structure, with a large metallic core and a silicate mantle, is reminiscent of the terrestrial planets in our own solar system. However, its relatively close orbit, combined with the brightness of its host star, implies that it is subject to substantial stellar irradiation, which could, in theory, strip away any residual atmosphere over time. Spectroscopic studies have not yet shown any major signs of an atmosphere, which supports the idea that HD 219134b is mostly just a rock. Because it doesn't have any volatiles, it's a great place to study how atmospheres are lost and what makes a hard world able to keep an atmosphere in places with a lot of radiation. The results show that even if there was a primordial atmosphere when the planet was first formed, it may have been totally worn away by later processes like photoevaporation and thermal escape, leaving behind a dense, compact core. Most scientists think that the planet formed in a part of the protoplanetary disk that had a lot of solid materials. This let it build a strong core before the gas in the disk disappeared. On the other hand, it might have had a thin atmosphere at first, but the high energy flow from its host star may have quickly destroyed it. Its high density is due to the fact that the processes of differentiation have clearly separated the heavy elements, as shown by detailed models of its internal structure. These new ideas are very important for improving our models of how terrestrial planets form, especially in cases where starlight is the main factor. HD 219134b's proximity to Earth makes it a prime target for follow-up studies using both ground and space-based observatories. Future investigations will aim to detect any trace atmospheres or exospheric components, which could provide additional clues about the planet's evolutionary history. Nu-2 Lupy D, the moderately massive sub-Saturn. As an interesting example of a world that is somewhere between super-Earths and gas giants, Nu-2 Lupy D stands out. This planet, which is a sub-Saturn, doesn't fit the usual pattern of either low-mass rocky worlds or huge gas giants. Its properties challenge standard models of how planets form. Nu-2 Lupy D's features give us important information about the range of events that can happen during planet creation. It has been called the moderately massive sub-Saturn. In terms of mass and radius, Nu-2 Lupy D is right in the middle of normal super-Earths and full-on gas giants, according to observations. Its middling density suggests that it has been able to build up a large gaseous shell while still keeping a large core of heavy elements. The simple idea that planets must either be mostly rock or mostly gas is challenged by this one-of-a-kind mix. Instead, Nu-2 Lupy D seems to show a range of possible planet results, which are affected by the conditions in its protoplanetary disk. The measurements indicate that while the planet's envelope is not as massive as those of typical gas giants, it is sufficiently extended to impact the overall density significantly. This intermediate state implies a formation history in which the planet may have begun accreting gas before the protoplanetary disk dissipated, but the accretion process was later curtailed, perhaps by a reduction in available disk material or by competitive formation processes in a crowded planetary system. More information about Nu-2 Lupy D's atmosphere can be learned from spectroscopic studies. Its transmission range shows that it contains common volatiles like methane and water vapor, as well as heavier elements that point to enrichment processes happening during creation. These findings suggest that the atmosphere changed over time, with gas buildup happening first and then some atmosphere loss or chemical difference happening later. These changes make the atmosphere neither as thick nor as thin as one might expect from a super-Earth that has been stripped of all its atmosphere. Residing in a multi-planet system, its orbit exhibits slight eccentricity and moderate separation from its host star, factors that likely influenced its ability to retain an envelope while undergoing migration. The interactions with neighboring planets may have induced modest tidal heating, further influencing its thermal evolution and atmospheric dynamics. These processes underscore the complexity of planetary system evolution, where gravitational interactions, disk properties, and stellar irradiation all play interdependent roles. K2-229b, the Iron Planet. K2-229b is an amazing example of a world that has surprised scientists by having a very high density and a lot of metals in its makeup. This world, which has been called the Iron Planet, is thought to have a core made mostly of heavy elements. It may have a large iron-rich core that makes it look like a bigger version of Mercury. Scientists are rethinking the processes that can cause such extreme differences during planet formation, because observations show that its total density is much higher than that of most rocky exoplanets. The fact that K2-229b is in a very tight orbit around its mother star is what makes it so interesting. The planet's circle takes less than a day, putting it in direct contact with strong star radiation and tides. Under these conditions, the atmosphere should normally be stripped away, and the surface of the planet should even change due to high burning. However, this world's high density suggests that if it ever had a thick layer of volatiles, those layers have long since been worn away, leaving behind a core that is bare and highly varied. Astronomers have been able to measure K2-229b's mass and radius with great accuracy thanks to detailed spectroscopic and photometric studies. Based on these measures, its mass is about the same as other super-Earths, but its radius is much smaller, which suggests that its core is dense with metals. The usual core accretion model says that planets with enough mass should be able to keep at least a thin atmosphere. This finding calls that model into question. For K2-229b, the planet's closeness to its host star seems to have caused it to lose all of its volatiles, making its rocky metal core stand out even more. There is a lot of disagreement about how K2-229b came to be. It's possible that it started out as a normal rocky planet that lost any basic atmosphere it may have had due to strong stellar irradiation and tidal stripping. K2-229b could have formed in a place that was naturally high in heavy elements, which would have let it quickly form a big iron core before a lot of gas could be accreted. Any way you look at it, the planet's current state says that it went through a very different kind of evolution than what is usually suggested by models of how planets form. The harsh conditions of K2-229b's orbit change both its chemical makeup and its heat qualities. Because the world is tidally locked, one hemisphere has sunshine all the time, and the other has darkness all the time. This makes big differences in warmth across its surface. The strong light from the stars probably raises the temperature on the day side to a point where silicates melt, while the night side stays much cooler. If there is still some atmosphere left over, these kinds of temperature differences can cause the atmosphere to move quickly, even though the general signal shows that almost all of the volatiles have been lost. Using telescopes in space to look at K2-229b's surface has given us new and important information about its chemical makeup. The spectrum fingerprints show that iron and other refractory elements absorb light very strongly. The results back up the idea that the planet's surface is mostly made up of metals and silicates, similar to the inner rocky bodies in our own solar system. But K2-229b is different because it doesn't seem to have any lighter elements that would indicate a thick atmosphere. Astronomers need to improve their models of atmospheric erosion because of this clear difference, especially for worlds that are exposed to very high levels of radiation. K2-229b serves as an important benchmark for understanding how planetary cores evolve after the loss of their primordial envelopes. The fact that such a planet exists and remains stable in an ultra-short period orbit suggests that there may be a broader spectrum of outcomes for rocky exoplanets than previously thought. Its existence forces theorists to revisit the interplay between stellar radiation, tidal forces, and the efficiency of atmospheric stripping. Furthermore, it provides an opportunity to study the end stages of planetary evolution in a system where the expected gaseous envelope has been completely removed, leaving behind a naked core. LHS 3844b, the Bare Rock. LHS 3844b is an interesting and mysterious world that has been called the Bare Rock because it doesn't seem to have a major atmosphere. This planet, which is about the size of Earth, is orbiting a nearby M-dwarf star. It is a stark example of atmospheric erosion and shows how evolution can strip a planet down to its rocky core. Many of its neighbors are able to keep their thick atmospheres, but LHS 3844b looks like it's just a rocky shell left over. It's a great place to study how strong star irradiation can wipe out a planet's volatile envelope. The orbital period of LHS 3844b is very short. It goes around its host star once in less than a day. Because it is so close, the planet is constantly hit by high-energy radiation and star wind from its busy M-dwarf host. Over time, these forces have probably been strong enough to wear away any atmosphere that LHS 3844b may have had in the past. The fact that there are no visible atmospheric signs in its broadcast spectrum says that the planet is mostly made up of rocks and has almost no gaseous envelope left. The planet's mass and radius have been carefully estimated using transit photometry and radial velocity methods. The density of the planet's material supports the idea that it is mostly made up of rocks. This high density shows that LHS 3844b is mostly made up of hard materials like metals and silicates. Due to the lack of volatiles, it seems likely that the planet's atmosphere either never existed or has been completely destroyed by photoevaporation and heat loss. Existing models usually say that planets this big and in similar paths might still have a light atmosphere. But this extreme case of losing an atmosphere calls those models into question. The background of how LHS 3844b formed is just as interesting. It's possible that the planet formed farther out in its protoplanetary disk, where conditions were better for keeping a gaseous shell. But later, movement inward would have exposed it to much stronger radiation, which would have caused the atmosphere to quickly wear away. Another possibility is that the planet formed itself in a way that encouraged the buildup of heavy elements over fragile ones. In either case, the planet that is left behind has almost no atmosphere at all. It is a bare rock that shows how deadly star radiation can be. It is believed that LHS 3844b will have very high temperatures. Because of tidal locking, one side is always facing its star. This means that the day side is probably very hot, with temperatures high enough to melt things, while the night side is much cooler. If there is still heat inside, this huge difference in temperature can cause violent surface processes like thermal fracture or even limited volcanic activity. Since there is no atmosphere, these temperature differences are not tempered by heat transfer. This gives a clear picture of the conditions on the planet's surface. many spectroscopic studies have not yet found any major air components. This strongly supports the idea that LHS 3844b is indeed a bare rock. Since there are no signs of water vapor, carbon dioxide, or other molecules being absorbed, it looks like the planet's shell has been totally worn away. This finding has huge implications for how we think about how low-mass exoplanets, especially those that circle active M-dwarf stars, keep and lose their atmospheres. It also makes us wonder if similar worlds might be habitable. If air erosion is common in those kinds of systems, then the time for life to form may be a lot shorter than we thought. The orbital dynamics of LHS 3844b offer valuable clues about the long-term evolution of close-in rocky planets. Detailed measurements of its transit timing and orbital stability indicate that the planet has maintained a consistent orbit over the timescales accessible to current observations. This stability, despite the harsh conditions it faces, suggests that once an atmosphere is lost, the remaining rocky core can persist in a state of equilibrium, albeit one that is inhospitable to life as we know it. As we conclude our exploration of these extraordinary worlds that defy the odds, we are left with a profound reminder that the universe is an ever-evolving tapestry of unexpected wonders. The planets that shouldn't exist yet do not only upend our theoretical frameworks, but also ignite our curiosity, urging us to question what we know about cosmic creation. Join us in continuing this journey of discovery. Subscribe for more deep dives into the mysteries of the cosmos, and share your thoughts on how these defiant planets reshape our understanding of the universe.